Hi ladies and gentlemen, in this video we learn about the autocorrelation and power spectral density. So let me start with that presentation. So this short speech is organized into your learning outcomes about autocorrelation and its properties and the summary of understanding. So you will learn about the autocorrelation of a WSS process, and then you will learn the properties of autocorrelation function, and then you will understand the relation between autocorrelation and power spectral density. For a WSS process xt, the autocorrelation function is defined as Rxxt, Xx meaning that it's an autocorrelation, not a cross correlation like XY. It is Rxx. Tau is that it's a time shift, that is expectation of xt x t plus tau. This function is an even function like Rxx tau. It is symmetric. It's an even one, symmetric around the origin. So Rxx tau is Rxx minus tau. This can be easily proved because Rxx tau is expectation of xt plus tau. If I make a substitution for t plus tau, that is, if I say if I let t plus tau is equal to say t1, so Rxx tau becomes expectation of xt1 minus tau, because that is a first term. This t is now t1 minus tau into xt1. Okay. Now this is same as this is nothing but the equation for Rxx minus tau. Expectation of xt1 t1 minus tau. This is nothing but Rxx minus tau. So we can easily prove that Rxx is an even function. The autocorrelation is an even function. Again, the second property is that the maximum value of the autocorrelation function is at the origin. That is, Rxx0 is greater than or equal to Rxx tau for every tau. So this also can be very easily proved. I can take the expectation of xt plus or minus xt plus tau whole square. Okay. Since this xt plus or minus xt plus tau whole square is greater than 0, the expectation value should also be greater than or equal to 0. So this equation is greater than, or this this expectation is greater than or equal to 0. If I expand this equation, it becomes expectation of xt square plus expectation of xt plus tau whole square plus or minus twice the expectation of xt plus tau. This should be greater than or equal to 0. Now these first two terms are nothing but the autocorrelation function. It is Rxx tau, and this is my this is my Rxx0, and this is my Rxx0, because it is essentially the same thing. So it is twice Rxx0 plus 2 times Rxx tau, because this is Rxx tau, this is Rxx0, and this is Rxx0. This is xt square. Expectation of xt square is Rxx0. This just delayed by advanced by tau units. It is nothing but expectation of x some t dash square, which is also Rxx0. So it is twice of Rxx0 plus or minus twice Rxx tau, that is greater than or equal to 0. So since it's a plus or minus thing, I can say that on transposition this becomes Rxx0 greater than or equal to modulus of Rxx tau. And Rxx0, that's the maximum value, which is nothing but expectation of xt square. And there is another very useful term that is called the power spectral density. That is a Fourier transform of the autocorrelation function. Usually it is denoted by Sxxf. This is a function in the frequency domain. So Sxxf, that is minus infinity to infinity Rxx tau e raised to minus j2 by f tau d2, the self same equation for Fourier transform. And the inverse equation will be Rxx tau is minus infinity to infinity integral Sxxf e raised to j2 by f tau df. This is the inverse equation. This is the inverse Fourier transform equation. Now the interesting case happens when tau equal to 0, that is Rxx0, that is nothing but integral minus infinity to infinity Sxx f df. What is this Sxx f? That is the power spectral density. So if I integrate this power spectral density over all frequencies, this gives me the signal power. So Rxx0 is nothing but the signal power. There is a power in the signal xt. That is the meaning of Rxx0. This is a relation between Rxx2 and Sxxf, the relation between this is a famous Wiener-Keynesian theorem. So the power spectral density is a Fourier transform of the autocorrelation function. Now coming to the end, you learned the autocorrelation of WSS, then you understood the properties of autocorrelation, then you understood the relation between autocorrelation and power spectral density. And that is the end of this presentation. I thank you all.